Hello. Let's look at some, just like in general, how to apply calculus to physics. So, uh, so your standard formulas that you might memorize when you're learning physics, just some examples of standard formulas, would be displacement equals velocity times time, velocity equals acceleration times time, work equals force times displacement, and force equals mass times acceleration. So in all these examples, you'll see that we're saying that some quantity equals two other quantities multiplied together, and by extension, you could divide through by one of the terms and get some quantity equals to another the quotient of two other quantities. And you can see that for any of these examples. And if we look on the right-hand side here, what I've drawn is three um, graphs where you have time on the x-axis and you have some function of time on the y-axis. The first one is position versus time, velocity versus time, acceleration versus time. And um, so just to give some values to these, they don't have to have values, but let's just give them values. Let's say the first one is x squared, the second one is 2x, and the third one is 2. Now we see that the derivative of x squared is 2, the derivative of, is 2x, I should say t, is 2t, the derivative of 2t is 2. And going in the reverse order, assuming that the initial velocity value is 0 and the initial position value is 0, then the integral of 2 is 2t. The integral of 2t is t squared. And so kind of just to show there that these relate by derivation and integration. And so what's kind of handy here is, so what that means is velocity. So let's take a look at this example down here. We say that velocity equals acceleration times time. Well, in this example right here, we also see that this length is time, this length is acceleration. So velocity actually equals the area under this curve, because acceleration times time is the area under this curve. And in these other two examples, if we were to take, so displacement equals velocity times time. But if we were to take velocity times time, and like take this max value, for example, we would actually be finding the area under this curve, which is not the same as the area under the initial curve that we had. So it's not actually going to give us our position. It's going to give us the position if velocity equaled, well, 2, as it did down here, or just some constant number. And actually, basically what's going on there is this holds true if velocity is constant. And if time is constant, but we kind of typically think of time as being constant. So let's just say if velocity is constant, then this holds true. Okay, if it's not constant, then what you'd have to do is the integral, because the integral gives you the area under this curve. So to get from displacement equals velocity times time, to get from this graph to this graph, you would actually take displacement, which here I made an x instead of a d, but I mean displacement, equals integral from the initial independent variable value to the final independent variable value of velocity as a function of time times dt. And so what I like about this, I think what's kind of convenient, is that so displacement equals velocity times time, and to apply calculus, it's basically just displacement equals the integral of velocity times dt. So there's still like this multiplication thing going on in there. Velocity equals acceleration times time. However, if acceleration is not constant, you'd have to use velocity equals the integral of acceleration times dt. And you can actually use this even if it is constant, it'll still give you the same answer. So on the right hand side, you can use these if it's changing, but probably the easier way to explain this is in terms of instantaneous versus average. So velocity equals displacement times divided by time. Well, if I take displacement here and divide it by time, like say with these two values on the end, what I'm actually going to find is that this is the velocity, and we could see that actually at no point during this time value, well, no, that's not true. At some point, probably graphically, it looks like maybe at this point right here is where that's true, but it's not true at every point. So basically, what we're actually finding is the average velocity. The average velocity equals the displacement divided by time. If we wanted to find the instantaneous velocity at any point, what we're really finding is the tangent line to that point. So we'd be finding dx divided by dt instead of just d divided by t. And the same holds true in these other two graphs. The difference is in these other two graphs, the rate of change is actually constant, so that the average value equals the instantaneous value. Okay, so now let's take a look at this little chart I have right here. So one thing that's kind of cool here, I think that a great deal of calculus is actually learning how to multiply, and that's not technically correct, but I think it's fun to think about, and it's close to being true, because technically this integration is not the same as multiplication. It's more like a substitute for multiplication, but at any rate, it's kind of like learning how to multiply. So what I mean by that is, if let's just take all these relate to work, right? So work equals force times displacement. This only holds true if both force and displacement are in the same direction, and force and displacement are both constant over the duration where you're considering the work being done. And so to explain what I mean by same direction, or in this case 180, same direction or 180 to each other, everywhere I said same direction, 180 is also counted as the same direction for this purpose. So force and displacement are both vectors, which means they have both magnitude and direction. So when you say that work equals force times displacement, that only holds true if work and displacement point in the same direction, or if force and displacement point in opposite directions. If force and displacement point neither in the same direction nor directly opposite to one another, then you actually have to use this down here, dot product. So this is work equals F dot D, and it's more or less a different way to do multiplication that I'm not actually going to talk about any more than that in this video. Now, as shown over here, if force or displacement changes during the duration of the work, you're going to have to set up an integral. And this is just a simplified way, one possible way of setting up the integral. Often the ways that you would set up the integral get kind of complicated on how to set them up, and it varies from situation to situation, but this is an example. But it will be an integral anyway, so use integration if it's the same direction, but they're non-constant, meaning that over the course of the work being done, either one or both of the variables, force or displacement, change. Now, the next thing applies to division, which I already talked about over there. So force equals work divided by displacement. This only holds true if you're finding the average work over the duration, or if the ratio is always the same, meaning that it's when you graph them, you get a straight line. It doesn't have to be directly horizontal. If it's directly horizontal, actually the force would be 0, but it's at some straight line as opposed to a curved line. So the straight line version will also give you the instantaneous force, but if it's not a straight line, then this setup will actually give you the average force. If you want to find the instantaneous value and you do not have a straight line, then you need to use force equals the derivative of work with respect to displacement, or again, however you choose to put your dependent and independent variables. So now let's consider some somewhat contrived examples that won't be 100% correct, but will be, I think, good for illustrative purposes. Okay, so let's take work here. Work equals force times displacement. Let's imagine some scenarios where either force is not constant or displacement is not constant. So let's say that we have, first of all, force is equal to mass times acceleration. So what we actually have is work equals mass, and if I put the vector notations, because acceleration is a vector and displacement is a vector. You don't need them though, not for what I'm doing right now. I'm assuming the same direction. So let's say that work equals mass times acceleration times displacement. And let's say that we have this situation with this hill and this snowball sitting on the hill, and this is a cartoon, so we're going to obey cartoon physics here a little and not necessarily real physics. As this snowball rolls down the hill, well, what happens in a cartoon? The snowball grows. So if that's true, I'm not sure. I think that can maybe happen in real life sometimes. I'm not sure. I know it definitely doesn't always happen. Maybe it never happens. I'm not sure. But in the cartoons it happens. So let's say for the sake of argument that it's happening in this situation. So in that case, work equals the things that do not change. The mass does change. The acceleration does not change. And here I'm going to set up distance as the distance does not change, and I want distance to be the, or displacement, I want displacement to be the independent variable, so maybe this would be better had I made this an incline like that. My setup will be slightly more accurate if the incline had looked like that. And so we want this to go from the initial distance displacement value to the final displacement value of mass as a function of displacement dd. So this is possibly a setup that you could use to find work under these circumstances. Although these setups I'm going to do right now are not necessarily the setup that you would want to use to solve for these things, but they're just meant to point you in the right direction, to show that you would use an integral. The actual setup of the integral may end up being different from my examples here. Let's say now an example where, so that's where mass is accelerating and mass happens to be increasing. An example where mass would be decreasing would be a rocket. So let's say we have this rocket, and as the rocket lifts off, it's burning this jet fuel. And in a rocket, the jet fuel, the weight of the jet fuel is not inconsequential, it matters. So as this is burning, the weight of the rocket is changing, the mass of the rocket is changing. So in this case, work equals, if we're still close to the Earth, acceleration is not changing. The integral, the initial displacement value, final displacement value, mass is a function of displacement, dd. So displacement is changing, but displacement is changing at a constant rate. You're constantly going up by the same amount, conceptually how we're imagining this. Mass is changing, but mass is changing at a variable rate. So the amount of mass that's changing is not, we're not thinking of it as the independent variable. So like time, conceptually when we tend to think about time, we tend to think of it as ticking along regularly. And then if something happens during the duration of that time, it may be wild, it may be smooth. You have no idea until you actually figure out the equation. That's kind of what I mean here by, because technically the way I set this up, we imagine displacement changing, but the displacement, it's not really that the displacement's changing, it's more like it's changing at a regular interval. And if I went into some notation, it would make more sense what's going on, but I just don't want to do that for this video. So, so we have mass changing. We can imagine acceleration changing if we have, so let's say there's this big planet and this little asteroid that's really far away, and this asteroid's going closer to the Earth. We know that the force of gravity here, big G, is going to be the inversely proportional to the square of the distance or the displacement. So I think distance, I'm not really sure. Anyway, so if we wanted to calculate work here, we're going to have the acceleration changing. So maybe you could say work equals the, let's say the mass of the object is constant times the integral of some initial displacement value to some final displacement value of the acceleration as a function of displacement, because we imagine displacement ticking along at regular intervals, dd. So this is kind of like the ballpark idea of how you could start to apply calculus. This may not actually get you to the right answer, but it's kind of like, I think conceptually, a good way to think of applying calculus. The details get a little messier depending on the exact problem. So one more example maybe where we imagine distance changing. My last example will be an example where I imagine force changing, but I've actually done the same problem other times where I imagine yeah, we'll skip that. So for an example where displacement changes, actually they set that up different. That's enough of those examples. Let me go to a specific example that I'll actually work out. And this is my final little bit here. This example that I want to work out is an example that I've worked out in other videos. However, I did them a little different. I think I thought of it more in terms of a math problem instead of thinking it from a physics starting standpoint. And also in this standpoint, I want to work to the graph first and then solve it. I just feel like doing it that way. So let's say we have this building here. And there's a pulley on the building, a little man on the building. He has this rope that hangs down over the edge of the building. The length of the rope that is hanging down is 20 meters. The linear density of the rope is 2 kilograms per meter. Okay, so first off, if we imagine what's the full mass of this rope, the full mass of this rope is going to be 2 times 20, so it's going to be 40 kilograms. So we have a 40 kilogram rope that we're pulling up the side of a building. So we might say that work equals force times displacement. Force times displacement. And we might say that force equals mass times acceleration. So we're going to have work equals, we'll leave units out just for space here and time. So work equals 40 kilograms times acceleration 9.8 meters per second squared times a displacement of 20 meters. What we're actually doing when we solve this is, so let's see, we have, here's a 10, here's a 10, so we have 10 squared, so 10 squared, 9.8, 980, doot doot, and then times 8, that's going to be hard to do, well, so that should be 1,000 times 8, 8,000 minus 8 times 20, which is 8 times 20, it's going to be 160. So, well, 8,000 minus 160 should be 8,000. So we're going to have 7,840 joules. Let me check that with a calculator. So we have 40.8 and 20. 7,840. Okay, so I figured that work equals 7,000 840 joules. But what have I actually calculated? This would be the situation where we have this block whose mass, okay, imagine it's a block. There. All right, so imagine that's a block. We have this block whose mass is 40 kilograms. And we raise this block up 20 meters. How much work have we done? That's what we just calculated, 7,840 joules. But you'll see the problem here is, in this example, the mass, and therefore the force, is actually changing, because the very first time we pull up, well, so it'd be 2 times, our force would be 2 times 9.8. I'm going to leave the 9.8 because the 9.8 is always the same. So the first moment, sorry, not, yeah, our mass is changing. Well, technically the displacement's changing. I know that you can think of it also as, okay, so the first time we pull, we have 2 kilograms per meter. No, yes, it is the mass that's changing. We have 2 kilograms per meter times 20 meters that we're pulling, right? That's the mass that gives you kilograms. So our initial pull, we have 40 kilograms that we're pulling up the side of this building. However, what you'll notice is that's for the very, we do end up pulling that entire weight up, but our that's like our last amount that we pull. Our first amount that we pull, like the first meter, is actually going to be 2 kilograms per meter times 1 meter. We're pulling up 2 kilograms initially. Then when we go to the second meter, we're pulling up 2 kilograms per meter times 2 meters. We're pulling up 4 meters, and so on, and it keeps rising. And you might have noticed that from what I'm saying that we're rising at a steady rate. So the rate that we're rising is 2 kilograms per meter. That's the rate that the mass is changing. And if we want to set this up graphically, there's probably easier ways to do this initially, but I think I really like this way because it's going to relate to what I started with, these graphs over here. So we're going to set this up as a force versus displacement graph. And initially we want to imagine that we're pulling up 0 kilograms times 9.8 meters per second squared. That's our force, is 0 newtons. And we're going to keep pulling, and let's say we don't know the shape yet. We're just going to keep pulling until we get to the end, which is going to be 20 times 2 kilograms per meters, which is 40 kilograms. 40 kilograms times 9.8 meters per second squared. 20 times 9.8, that's 98 times 2, that's 200 minus 4, it should be 196. 196 newtons is our final value for the force. Our initial value for the force is 0 newtons. And what you'll notice is this steadily increases from here to here. If it's steady, it means it forms a straight line. And the reason for that is every meter that we pull, our mass increases by 2 kilograms. So for the first meter, it's 2 kilograms of mass. The second one, 4 kilograms. Then 3 kilograms. Then 4 kilograms. It's a steady increase of 2 kilograms for every bit that we pull. And if it's a steady increase of 2 kilograms, it's a steady increase of 2 times 9.8 newtons. 2 times 9.8 should be 19.6. So our function for our force over displacement is actually equal to 19.6 times d. And this value down here, our displacement goes from 0 to 20. So this is 20 meters. And we can actually calculate work from this graph without applying calculus. So let's do that first and then check our answer after using calculus. So right now, we know that our answer should be the area under this curve. So to find the area under a triangle, well, most people know how to do that. It's work. So in this case, it's going to be 1/2 base times height. So 1/2 of 20 is 10. 10 times 196 is 1,960. 1,960 joules. So work equals 1,960 joules. But at this point, I haven't really applied calculus. This just happened to be an easy one where I could apply geometry to the graph. But let's say that I could come up with this function for force as a function of displacement, but maybe I didn't know how to or didn't want to calculate the area under the curve using geometry. I can apply calculus to this and set it up, and it will give the answer as well. I think I made, this is 19.6. You know what, that was supposed to be 392. I got 196 here. How did I get that? Force equals mass times acceleration. The mass is 2 times 20, 40. 40 times 9.8. Let me check that real quick. I don't think that I... Yeah, oops. This was supposed to be 392. Darn. 392 newtons. Which makes this down here. Let me just erase all that. Oh. I was doing that in my head, so I'm not sure what I did there. But this is supposed to be 392 newtons. This is actually correct right here, so I think I did a multiplication error. 392 No, that was right. This is supposed to be 196. Darn it. Alright. This is supposed to be 196. No, it is 392. Wait a second. Not sure where I made my mistake now in my recording, but this was supposed to be 392. So 1/2 base times height. 20 divided by 2 is 10. 10 times 392 is, so we have work equals 3,920 newtons. So hopefully people watching this caught my mistake when I did that. I think I made a math mistake in my head when I was trying to do that. Yeah, I got 196 instead of 392. So now let's set this up as an integral, even though we already have the answer. And actually you'll notice that that's joules. Not newtons. Newtons is force. Okay. This is supposed to be joules. Alright, 3,920 joules. And this one, should be bigger. This one was 40 kilograms times 9.8 times 20 I think I did check that. 40 times 9.8 times 20 is 7,840. So it took 7,840 joules of work to carry this box up. Why is that? Yes, okay, because during the course of, if we imagine this the other direction, then the amount of mass is decreasing over time. Because if you imagine that initially you're pulling the whole mass of the rope up, and then as time goes on, you're pulling less of the mass. So first you're pulling up 20 meters of the rope, then you're pulling up 19 meters of the rope, then you're pulling up 18, 17, and so on, all the way down to your last little pull where you're pulling up, 1 meter of rope. So the mass is decreasing over time. So the you could also think of it as the displacement is changing, and technically we don't ever actually pull the full mass of the rope the full distance. We only pull, anyway, if I were to have set it up different, you could think of the displacement as changing if you were to do it the normal way and break this up into little disks. Anyway, so let's set this up as an integral now. I have found a formula. I have found force as a function of displacement, so now I can set this up as an integral. Work equals the integral from the initial displacement value, which is 0, to the final displacement value, which is 20, of 19.6 times d dd, which is going to be work equals 19.6 times d squared over 2 minus d squared over 2 evaluated from 0 to 20, when this is going to be 0. So we're just going to have 20 squared over 2. We can break this into 2 times 10. So 2 squared is 4. 4 divided by 2 is 2. Then we're going to have 10 squared. So 1960. 1960 times 2, which I should probably do that on a calculator at this point. My brain's getting a little tired. So 1960 times 2 is 3,920. So work equals 3,920 joules. So you see we get the same answer. Conceptually, the way that this problem is also done, so here I chose to set up a graph first, and I set it up as a graph of force as a function of displacement. You could also do this problem by saying, let's say this is the top of the rope, this is the bottom of the rope. You imagine slicing the rope into these tiny little pieces, and you'd actually probably call this dm, which is going to, then in this case you imagine that the height goes from 0 to 20, so you'd have probably, let's see, work equals well, just for this dm, so dw, that means the work for this little tiny piece is going to be equal to dm times g, which is acceleration, times displacement. So yeah, they still had actually masses though. So then you're going to go work equals integral from d initial to d final of g, which is 9.8, times when does the 2 come in? So 2 is supposed to be part of the mass, because the mass is actually that's what I didn't figure out. So it's going to have to have the other times 2, which is the linear density, times d, which is the distance, dm. So this you see then is the same. Hopefully that was clear enough. I was a lot messier on my explanation for that. So there's just some kind of an overview and then maybe a little bit of specific examples of applying calculus to physics.